This video is looking at thin film interference using an online simulation. So when you first open up the simulation, there are several things to notice. First, on the left side, there are different representations of the waves. So we have the incident wave, the reflected wave, and down at the bottom, there is the combined wave from the front and the back reflections. So this one is going to be important as when you run the simulation, this is the wave that you will use to judge whether you have constructive interference, destructive interference, or neither. And over on the right, we have several different sliders. These allow you to change the various settings among the simulation. So you can select the slider with your mouse and then either lower or raise the value. And if you want to do the fine adjustment, so to figure out what the smallest scale division is, you want to use the right and left arrow keys. So by using the right and left arrow keys, you can see that the smallest division for the wavelengths is 1 nanometer. So you'll want to use that smallest division of the scale to determine an appropriate uncertainty for that value. And it would be safe to use half of the smallest division on the scale. And just as a fun effect, you'll also notice that the wavelength changes color corresponding to the wavelength in the visible range. So right now it appears blue, and as we increase the wavelength, we get green, yellow, orange, red, and now we're outside of the visible range. You can also change the index of refraction of the 3 mediums. So in front of the thin film, inside of the thin film, and then behind the thin film. And again, you can click on the scale, and if you want to determine the smallest division, use the left or right arrow keys to decrease or increase the value, and you can see what the smallest scale division is. That will allow you to make a reasonable uncertainty estimate for that scale. So now I've clicked on the thin film scale, and I'm just using my arrow key to increase the value, again by the smallest division. And for the third scale, again, I can use my arrow keys, and all 3 scales have the same smallest division, so you may use the same uncertainty for all 3 scales. And then the last scale controls the thickness of our thin film. So again, you can click on it with the mouse, then you can use that to lower or raise the value, or you can also use the left and right arrow keys. And again, consider the smallest division on the scale and use that as part of your uncertainty estimate for the value. Now, in the first part of the experiment, we are going to have a thickness of 506 nanometers, and that is going to remain constant for steps 1 and 2. And we are looking for wavelengths in the visible range, which is 400 to 700 nanometers, where we have total constructive and total destructive interference for particular indices of refraction. And we want to have the one in front to be air, so it's set to 1.00. We want N2, the thin film, to be 1.8. And then behind the thin film, we want to have an index of refraction of 2.5. And what we want to do is start at 400 nanometers. And we want to run the simulation. So we want to judge the combined wave here and estimate whether or not we have total constructive or total destructive interference. And I'm just going to lower my wavelength a little bit until it is right at 400. So you can see the effect of lowering the wavelength actually increased the amplitude of the combined wave. So if I increase my wavelength again, I can see that the amplitude changes depending on the wavelength I've used. So what you want to look for is which wavelength gives you closest to total destructive interference, meaning this line is almost perfectly flat because the incident wave and the reflected wave perfectly cancel each other out. And it can be hard to determine exactly where that occurs. So if I lower my wavelength a little bit and increase it a little bit, I want to estimate exactly where do I get total destructive interference, and could I possibly increase or decrease the wavelength and still see that total destructive interference. Now, once I've determined my wavelength where that occurs, I'm going to increase it, and now I can see I'm getting close to maximum amplitude. And as I look at the amplitude of my combined wave, again, I want to try to estimate at which wavelength this amplitude is a maximum. And this one is a little harder to judge exactly which wavelength it occurs at. So again, if I can increase the wavelength just a little bit and it still appears to be a maximum, or decrease the wavelength a little bit and I still see a maximum, then you need to consider that as part of the uncertainty when you are recording the wavelengths at which you see your total constructive or total destructive interference. So that is an example of our first destructive and constructive interferences. And you'll just continue to increase the wavelength until you've found all possible wavelengths within the visible range where we get destructive and constructive interference. And then you want to select the appropriate equations from the theory section to predict what wavelengths these interferences, total constructive or destructive, occur at. And then you would want to compare your predicted and measured wavelengths for the various constructive and destructive interferences to see whether or not the values agree with an uncertainty. Once you get to step number 2, you're doing roughly the same thing, but you're going to change the material behind the thin film to air, so it's going to have an index of refraction of 1. And then you're going to repeat the process, so starting at 400 nanometers, and you're going to once again go through your wavelengths and look for places where you have total constructive interference, so the combined wave has a maximum amplitude, and total destructive interference. So the combined wave becomes practically a flat line. And again, using the appropriate equations from the theory section, calculating at which wavelengths these total constructive and destructive interferences occur, and then comparing our predicted and measured wavelengths. And then in part 3 and 4, instead of varying the wavelengths, we will use a fixed wavelength. So fixed wavelength of 602 nanometers. And we are going to change the thickness of our film for values between 50 nanometers and 1000 nanometers. And again, we're going to start with index of refraction behind the thin film at 2.5. And we want to, again, run through the various thicknesses and look for total constructive interference and total destructive interference. And again, compare those to the predicted values. And in part 4, you're going to switch the behind material back to air and repeat those measurements one more time and compare those again to the predicted values to see whether or not the predicted and measured wavelengths agree within uncertainty.